Oh, we're gonna do some physics right now, right now. Okay, so we are looking at some SOHCAHTOA examples here. So sine, cosines, and tangents. And before we get into that, I'd like to just talk about what it means to have a sine or a cosine term. Now, well, that's not what I want. If we take a look at just an axis here, and on this axis, we draw ourselves a lovely circle. Okay? In math classes, you often hear this called the unit circle, because what we're going to say is that this circle has a radius here of exactly 1. Now, if my radius is pointing up like this to the edge of the circle, I can actually think about breaking this green line up into 2 component lines, and these will be what we're calling our component vectors. Now, if I take a look at this, if I go on the x-axis, I can see that I can come over this way, and this will be the x amount of this green line here, okay? We see if we kind of bring this down, like this will be how far it goes in the x direction. If we go up, maybe that's a little high. Let's undo that one. If we go up, we're about right here. If we go up, we'll see that this green arrow reaches about this height right here. This would be the y direction here. Now, because these are vectors, and we will talk about this, we can actually shift the blue and red lines anywhere we want as long as we do not rotate them. So if we were to put them like this would be the same y line, and if we moved the red one up, this would be the same x line. Well, what you see here is you see a wonderful triangle we've just built, which is exactly what SOHCAHTOA is making use of. So what SOHCAHTOA is allowing us to do is if we have some arbitrary vector, some arbitrary arrow in space, we are able to find from it the x component of that vector as well as the y component of that vector. And if you watched the intro video a little bit ago, if we call this vector v and this is some angle theta, we can now go from a polar notation to a rectangular notation and vice versa. Okay, so that's what's going on here. The other cool thing with this unit circle is if we actually take the circle, there's our bell. If we take the circle and we kind of unroll it, so imagine that I took this circle here, I cut it at the bottom, and I unrolled it a little bit. So I took the bottom and I kind of flipped it around. What we would see is that this bottom piece, as I erase it, as I kind of flip it around, it'll come up and over, and then it'll kind of come, it would kind of look down like that. But if we actually draw this out, we're actually going to get a sine and a cosine graph. And a sine graph is going to look like that. And a cosine graph is, if I draw it correctly, cosine graph is going to look like, that's a pretty good one. That is a pretty good one right there. So this is a cosine graph, and this is a sine graph right here. Both graphs have maximums at 1, and they have minimums at -1, and they all pass through 0. The cosine graph is a sine graph. It just starts at a slightly different place. You know, if I backtrack it and I continue this, we can see how it's just a sine graph that's been shifted a little bit. But we're basically just taking a unit circle and we're kind of unturning it here to generate these graphs. With specific points being here being like 90 degrees or pi over 2, this being 180 degrees or pi if we're in radians, and this is pi over 2 if we're in radians. Here we've got 2, whoops, that's the wrong spot. Bloop, bloop, bloop. Here we've got 270 degrees or 3 pi over 2 radians. And at the very end, whenever this kind of kicks here and it would come up to here, this is our 2 pi, the whole 360 degrees. We've come back to where we've started. So that's what's going on with this unit circle. You're just saying, hey, look, how much of this are you in each direction, okay? Are you so much on the cosine graph? And are you so much on the sine graph? So if you were like out here, you know, how much are you on cosine, and then how much are you on sine? And that's what we're looking at, okay? So if we go down here and we look at some examples to actually figure out how we can break these triangles up based on what we have, we're going to apply a lot of what we did in the last video, but just using a little bit of math here, okay? So this time, if we look at example 1, we're given the angle down here. We know it's 34 degrees, and the first thing we'll do is we're going to label our sides. So we've marked our angle, and we're going to label our sides here. Going across out of our angle, this is the opposite side. Across from the right angle and the longest side is the hypotenuse, and this makes this our adjacent side here, okay? Now, if we would like to find x, this opposite side, we won't just circle it and say, there it is. We're actually going to find the quantity here. We're really looking for the opposite. So if we write out SOHCAHTOA, SOHCAHTOA, we're looking for the opposite side, which means we either need to use sine or we need to use tangent. We can't use cosine at all here. It doesn't have an opposite term in it, so it's out of the running for what we're going to use. The next thing we have to look at is, while we're looking for the opposite side, we only have this 13 in terms of quantities of lengths of the triangle. That's the hypotenuse. We have the hypotenuse. We don't in TOA, the tangent, so we can't use it. So we're stuck using sine, which is fine. To write this out, we write the sine of the angle. The sine of the angle. So the sine of 34 degrees equals the opposite, which is x, divided by the hypotenuse, which is 13. Now, it's important for us to remember that that sine of an angle, it is a function. So it's actually just going to return to us a number. And based off what we see with this unit circle idea up here, the number it has to return to us must be between 1 and -1. It has to be bounded by those quantities there. So this sine of 34 degrees is just a number. And if I'm solving for x, this means I just need to multiply each side by 13. And then I'll have 13 multiplied by some number will equal x. Now we want to be a little bit careful here when we do this. If we're using a calculator, something like this, we first need to make sure that we're actually in degrees. Most calculators start you off in radians. So what I'll do for a Texas TI 8384 is I'll click mode, and it'll bring up this screen. And then by going down, I'll switch myself into degrees. And then I'll quit out of that. If you're on a Texas TI 30 Mark X2 Solar Edition, you'll see a DEG in the bottom. That lets you know you're in degrees to begin with. But what I can do now, just to make sure I'm in degrees, is if I type in sine of 90, it is a well-known fact in mathematics that the sine of 90 is pointing directly up and it has a maximum value of 1. So if I hit enter, I get 1. That's what I'm looking for. Okay. So what I'll do here is I'll just say 13 multiplied by the sine of 34. And notice how the parentheses pop up in our calculator. We can close that, and then we can hit enter, and we're going to get 7.26. So our answer here is indeed for x. X equals 7.26. Okay? Now, if you're on your phone, what I recommend doing is do the sine first. What you actually have to type in on your phone, it's a little weird. You'll have to type in 34, and then you'll have to hit the sine button because the sine is being applied to the number ahead. You'll get a decimal out of that. If you take sine of 34 will give you 0.559. So if you type in 34, hit sine, and then multiply that by 13, that'll give you the 7.26 that you're looking for. Okay? So take a second here. We've got two other examples, example 2 and example 3, where you're solving for that unknown value x. Take a second and see if you can figure out how to set up both of these triangles and solve for this unknown value x given the angles. And you know your angles are up here at 67 and down here at 43. Okay, so pause the video, pause, try that out. You know, I'm not paused, I'm existing in real life, but you're paused and now you're seeing this. So let's get to it. Okay, if you haven't tried these, try them. You need to get good at this stuff. So as I'm trying this out and I'm looking at example 2 here, first thing I do is I notice my angle and I label my sides. So here is my opposite side, here's my hypotenuse, and this is my adjacent. If I'm looking at the classic SOHCAHTOA, so I'll write out SOHCAHTOA. I always like writing it out. SOHCAHTOA. If I'm looking for an adjacent, that means I'm eliminating sine. And if I only have a hypotenuse, that means I'm eliminating tangent. So I'm going to use cosine here. So I will say that the cosine of my angle, 67 degrees, equals, well, cosine is an adjacent over hypotenuse. So my adjacent is x, so x over the hypotenuse of 18. Now to solve this, I need to multiply each side by 18, because cosine of 67 is some number, and now let's try to crank that through. If you're using this on a phone, you type 67 and then hit cosine and then multiply it by 18. On this little calculator I've got set up here, I can type it truthfully. 18 times the cosine of 67. Hit enter, I get 7.03. You should be, if you're actually on a calculator, you should be actually just to type 18 times the cosine of 67. The calculator should know that that's a multiplication there, and it'll give you the same answer. So save yourself a little bit of a pen stroke. So that gives me 7.033 as my answer. So x equals 7.0, what was that, 7.033 or? Yeah, 7.03, okay? So that's my answer for that. For the second one, let's look at what we got. Same procedure, I've marked my angles. Let's get the sides. This is my opposite. This is my hypotenuse. I'm I'm across from the 90-degree line, and that makes this the adjacent. If I write out SOHCAHTOA, SOHCAHTOA, I'm looking for an opposite, so boink, boink. So cosine's gone. And what do I have? I have the adjacent, so I have the adjacent, which means sine is out. I'm using tangent. So let's set this up. The tangent of 43 degrees equals the opposite, because it's opposite over adjacent, so x over 9, multiply each side by 9 here, and we'll take 9 times the tangent of 43, so 9 tangent 43, close the parenthesis, equals, get 8.39. So x here, 8.39, 8.4, okay? If you're trying this on your phone and you can't get that, try entering in a different way. Some calculators are a little different in terms of how you have to enter that syntax or the order of operations there. And then you should get 8.39, 8.4 out of that. Now, I'd like you to do this for one more time, okay? One more time, pause this video and try it for this triangle down here, where we're given this angle, the 52, and this time we're looking for this value x up there. Okay, so pause the video. Come on, pause it. Pause it. Pause it. And then let's come back. So I'm going to approach this problem the same way, labeling all the sides. This is the, whoops, what am I doing here? That's not the hypotenuse. This is the opposite side. Duh. This is my adjacent, and this across from that 90 degrees is the hypotenuse. So let's write out SOHCAHTOA. SOHCAHTOA. Whoa, why did those O's and A's look so funky? That's an O and that's an A. So I'm looking for the hypotenuse. So boom, boom. Tangent, you out of here. What do I have? I have that 20, which is an opposite. Ooh, okay. So I can do sines. So what we'll say here is we can say that the sine of the angle that we base this all off of, 52 degrees, equals the opposite, which is 20, over the hypotenuse, x. So now we need to solve for this variable x. We need to be a little bit careful here. Oftentimes, we've gotten so used to just multiplying each side by the number that sometimes students will multiply by 20, but that doesn't make any sense. If you multiply by 20, you're going to get like 400 over here and then a random 20 on the left. That's not what you want. Some students look at this and they go, oh, I need to get rid of the 20, so they'll divide by 20. But that's also going to give you an issue. If you did do that, what you'd get is you'd get the sine of 52 over 20 equals 1 over x. And that's not what we want. I don't want 1 over x. I want x. I want the actual value. So I don't want this either. What we actually want to do is we want to bring x into the numerator on the left side, and we want to bring the entire sine of 52 down into the denominator on the right. Okay, so we're multiplying by x and dividing by the sine of 52. So that will give us x equals 20 over the sine of 52. And I know that feels weird to divide by like a word, like to divide by sine, but remember, sine of 52 is just a number. If you type into the calculator sine of 52, it's just 0.788. So you're really just dividing here by 0.788, okay? It's just a weird way of writing that. You'll also notice that if you accidentally divide it by the 20, this is just taking the reciprocal of each side. You're just kind of flipping them, okay? So 20 divided by the 0.788, let's just throw this into the calculator. So 20 divided by the sine of 52, close that parentheses, we're going to get 25.38 here, okay? And that's what we do want as our answer. So be aware of that. Anytime we're solving for something that is in the denominator, like we have here, we need to be a little bit more careful, a little bit more thorough of us doing this, just a little bit of algebra to make sure we're getting things on the right path, okay? And it's very common to just, you've done a bunch of these, you just keep doing the same thing, but this is the mix-up, okay? This is the curveball, this is the change-up. This is what's going to give you a little bit of a headache as you're rushing through problems, okay? But that is it in terms of using sine, cosine, and tangent. You know, if you have an angle and you have one of the sides and it's a right triangle, you can find information about your other sides using SOHCAHTOA. You know the values are going to be between -1 and +1 because of how the chart is set up. That unit circle is unfolded on itself. And, you know, as you're pushing these into the calculator, just be careful if you're using your phone or a, you know, Texas Instruments item of how your syntax is so you get those right, okay? But for that, this video is finished. Next time, we're going to look at how to find angles instead of sides. But until then, adios and take it easy.